Hello, and welcome to the short lightning talk about our recently accepted paper called Hierarchical Exploration of Continuous Seismograms with Unsupervised Learning. My name is René Steinmann, and I will give you a quick walkthrough about the main results of the study. So what is the aim of our study? Seismograms are a goldmine of information recording many different types of signals. And often as seismologists, we only use a small part of these signals. So we want to provide a tool which helps to explore the whole content of the data and possibly find patterns we haven't detected so far or we have overseen. And how could such a method or approach look like? So as the title suggests, we want to explore the data in a hierarchical fashion because we think that as seismologists, we also define signals in a hierarchical way. So for example, we can divide our signals in long and short-term signals. So that means we take the duration as a measurement and separate these signals. And then further, we can divide the short-term signals between earthquakes and explosion. And then the earthquakes, we could find local or regional earthquakes. So hierarchical clustering doesn't provide these tables, but it will also find families of similar signals. And then with this dendrogram, we can explore the data and find classes and subclasses of signals. So, and of course, the hierarchical clustering is only a small part of the whole data-driven approach. So basically, we have three main ingredients. So we take our continuous seismograms, which can be one component or three component, and we perform a set of wavelet convolutions, modulus, and pooling operation to create the deep scattering spectrogram. And from there, we extract the most important features with an independent component analysis. And these features then serve as a base for hierarchical clustering. To test our approach, we use data recorded in the vicinity of the North Anatolian Fault in Turkey. So on that fault, there was a small seismic burst happening with around 150 small magnitude events, which have similar waveform characteristics. And we use the data from the station nearby and try to identify the seismic burst within the dendrogram of the hierarchical clustering. So this is the main result. This is the dendrogram of the 2 days of continuous seismic data of a single station. And if we extract these 4 clusters, they won't give us labels, but we need to do an interpretation to give them labels we understand. So for example, cluster A, we interpret it as monochromatic seismic noise. Then we have urban noise such as traffic in cluster B in green, the ambient seismic noise in cluster C, and the seismicity in cluster D. So far, we didn't detect the seismic burst inside these 4 clusters, but we have a cluster of seismicity. So this suggests that if we would extract a finer cluster solution here, we might find a cluster related to the seismic burst. And if we do that, you can see we extract 200 events with very similar waveforms, and they correspond to the seismic burst. If you want to know more details about this study, I invite you to read the paper, or of course, you can also reach out to me, and I'm happy to discuss the method or maybe interesting data sets to apply to. Thank you.